Persian desert, where summer heat could kill an unprotected man in hours, ice formed in the night, not in mountains, not in hidden caves. In purpose-built structures that turned water into frozen blocks under a sky blazing with stars. By 400 BC, Persian engineers had mastered a technology that would not be replicated in Europe for another 2,000 years. They called them yakhchāls, ice houses. And they worked. The principle was simple. The execution was anything but. Across the arid plateaus of ancient Persia, from the edges of Mesopotamia to the foothills of the Zagros Mountains, civilizations rose in places that should not have sustained them. Water was the constraint. Water dictated everything. Where you built, what you grew, whether you survived the summer. The Persians understood this with a clarity that bordered on obsession. They engineered qanats, underground channels that moved water across impossible distances without losing it to evaporation. They designed gardens that defied the landscape. They created systems of irrigation so sophisticated that some still function today, 3 millennia later. But water alone was not enough. In a climate where temperatures could soar past 120 degrees Fahrenheit, preservation was survival. Food spoiled in hours, medicine degraded. The heat was not just discomfort, it was a constant enemy. And the Persians, with their characteristic ingenuity, looked at this enemy and asked a question that seemed to violate the laws of nature itself. Could they make ice where ice had no right to exist? The answer required understanding something most civilizations would not grasp for centuries. Heat was not a substance. It was the absence of something else. Cold was not a force you created. It was a condition you allowed. And the desert night, despite the furnace of the day, offered something precious. Radiant cooling. When the sun disappeared, the clear sky became a window to the void of space. Heat radiated upward into that void. Temperatures plummeted. In winter, they could drop below freezing. The yakhchal exploited this window of possibility with ruthless efficiency. Construction began with location. The structure needed to be near a qanat, or reliable water source, but positioned to maximize exposure to the northern sky while minimizing southern sun. The builders dug deep, sometimes 20 feet into the earth. The soil itself became insulation. Then came the walls. Not simple mud brick, but a specialized mortar called sarouj. Sand, clay, egg whites, lime, goat hair, and ash mixed into a composite that modern engineers still struggle to fully replicate. The proportions mattered, the curing process mattered. When properly made, sarouj became nearly impermeable to heat. Walls rose 6 feet thick at the base. The dome above them could soar 40 feet high, its shape designed to shed heat and create internal air circulation. But the walls were only part of the system. Adjacent to the yakhchal, builders constructed shallow pools, wide, flat expanses of water barely a few inches deep. As the sun set and temperatures dropped, workers filled these pools from the qanat. Then they waited. The night did its work. Heat radiated from the water's surface into the sky. The thin layer maximized surface area while minimizing thermal mass. Ice formed. Not everywhere, not always, but on clear winter nights, when conditions aligned, a sheet of ice would spread across the pool like glass. Before dawn, before the sun could reclaim what the night had given, workers broke the ice into blocks. They carried these blocks through small openings into the yakhchal's interior, down into the pit, into the darkness where the thick walls held the cold like a vault. Layer upon layer, night after night, ice accumulated, and once enough mass existed, the ice itself became an anchor. Cold preserving cold. The dome's shape created convection patterns that pulled hot air up and away. Ventilation shafts allowed precise control of airflow. The entire structure became a heat engine running in reverse. By the height of summer, when the desert surface baked and shimmered, the interior of a yakhchal could hold steady near freezing. Ice that formed in January remained solid in July. And the applications transformed Persian life in ways that rippled across the empire and beyond. Food preservation was the most obvious benefit. Meat that would rot in a day could last weeks. Fruit could be stored. Vegetables could be kept fresh for transport. This was not luxury. This was strategic capacity. An army that could preserve food could march farther. A city that could store provisions could withstand siege. Trade routes expanded because merchants could now transport goods that previously perished too quickly to be profitable. But the yakhchāls served another purpose that revealed the sophistication of Persian society: medicine. Ancient physicians, working within the humoral theory that dominated medical understanding, believed balance was health. Fever was excess heat. Heat required cooling. Ice became medicine. The ability to produce and store ice year-round meant treatments that were simply unavailable to other civilizations. Persian hospitals, some of the first dedicated medical facilities in the world, used ice for everything from reducing inflammation to preserving medicinal compounds. And then there was luxury, because ice was not just practical, it was impossible, and impossibility has always carried value. The Persian elite developed a taste for fallow-day, a frozen dessert made from thin noodles, rosewater, and lime, served with crushed ice. In the desert, in summer, the extravagance was the point. To serve ice to guests was to demonstrate mastery over nature itself. It was power made tangible, sweetness made political. The yakhchāls that served the wealthy were architectural marvels, their domes decorated, their interiors spacious enough to walk through. They were statements, monuments to human ingenuity and the wealth to command it. The knowledge spread. As the Persian Empire expanded under the Achaemenids, yakhchal technology moved with it. Regional variations emerged. In some areas, wind catchers, tall towers that funneled breezes into the structure, were integrated into the design. In others, multiple pools allowed for continuous ice production. The basic principle remained, but the execution adapted to local conditions, local materials, local needs. What's remarkable is not just that the technology worked, it's that it worked consistently across centuries. These were not experimental prototypes, they were infrastructure. By the time Alexander the Great invaded Persia in 330 BC, yakhchals were as common in Persian cities as granaries. The Greek accounts of the conquest describe them with a mixture of admiration and confusion. The Greeks understood ice, they had mountains. But ice in the desert, stored through summer, produced artificially from shallow pools. That seemed like Persian sorcery. It was not sorcery, it was thermodynamics. It was understanding heat capacity and radiant cooling and insulation. It was observational science translated into engineering without the formal language of physics. The Persians could not write the equations that governed what they built, but they understood the relationships. They tested, they refined, they scaled, and they created a technology that would remain unmatched in the West until the Industrial Revolution made mechanical refrigeration possible. The Roman Empire, which inherited much from the Persians through conquest and trade, never replicated the yakhchal. Romans collected snow from mountains and stored it in insulated pits. Expensive, labor-intensive, available only to the extremely wealthy and only in regions with mountain access. The Romans ruled an empire that spanned 3 continents, commanded engineering feats like aqueducts and concrete domes, and they could not make ice in the desert. The knowledge existed. Persian texts describe the process, but Roman engineers either did not believe it worked or could not translate the principle into their own context. This was not unique to Rome. Chinese ice houses operated differently, relying primarily on winter harvest and deep storage. Indian methods emerged later, possibly influenced by Persian contact, but never achieved the same scale or sophistication. Across the medieval Islamic world, as Persian knowledge was preserved and transmitted, yakhchals continue to function. They appear in texts from Baghdad to Cairo, always with a note of wonder, always with acknowledgement of their Persian origin. The longevity of the technology is perhaps its most telling feature. Yakhchals built in the 15th century still stand today, not as ruins, as structures. Their domes intact, their walls solid. In some regions of Iran, they were used continuously until the 1960s, when electric refrigeration finally made them obsolete. 2,000 years of operation. 2,000 years of producing ice where ice should not exist. 2,000 years of demonstrating that human ingenuity could rewrite the rules of environment and climate. But there is something else in this story. Something about the nature of knowledge and its fragility. The yakhchal was not a secret. The technology was visible, the structures dominated skylines. The ice was bought and sold in markets. Yet it remained functionally Persian for millennia. Other civilizations interacted with it, benefited from it, wrote about it, and did not adopt it. Why? Partly, it was context. The yakhchal worked best in arid climates with clear skies and dramatic temperature swings between day and night. It was optimized for desert conditions. In humid environments or regions with cloud cover, the radiant cooling effect diminished. The technology was not universal, but that does not fully explain the gap. Parts of the Mediterranean, North Africa, and Central Asia had suitable conditions. The knowledge was there, the need was there, the transfer did not happen. This pattern repeats throughout history. Technologies emerge in one context, prove viable, and then fail to spread despite obvious utility elsewhere. Sometimes it is cultural resistance. Sometimes it is economic inertia. Sometimes it is simply the difficulty of transmitting practical knowledge through text alone. You can describe a yakhchal, you can draw diagrams, but the crucial details, the proportions of sarouge, the precise angle of the dome, the optimal depth of the ice pool, these were learned through practice, through failure, through generational refinement. And that kind of knowledge does not travel easily. By the time European explorers and scholars began systematically studying Persian technology in the 18th and 19th centuries, the yakhchal was already fading. Colonialism brought new systems. Western ice, harvested from frozen northern lakes and shipped in insulated holds, became a global commodity. The ice trade, dominated by American and British companies, turned frozen water into an industrial product. It was expensive. It was inefficient. It required vast infrastructure and global shipping routes. But it fit the economic model of the age, and it displaced technologies like the yakhchal that required local knowledge and local materials. The first mechanical refrigeration patents appeared in the 1830s. By the early 20th century, ice could be made anywhere with electricity and the right equipment. The yakhchal became obsolete, not because it stopped working, but because the world changed around it. The technology that had sustained Persian civilization for 2 millennia became a curiosity, then a ruin, then a footnote. Except it was never just about ice. The yakhchal represented a way of thinking about problems. It was technology born from constraint. The Persians could not move mountains. They could not change the climate. They could not import ice from distant lands. So they looked at what they had, the night sky, the desert air, the earth itself, and they asked how these elements could be combined. They observed that water in shallow pools froze faster than water in deep containers. They noticed that domes created airflow patterns. They discovered that certain materials insulated better than others. They tested, they failed, they adjusted, and eventually they built something that worked so well it lasted 2,000 years. This was not the scientific method as formalized in the Enlightenment, but it was science, empirical observation, hypothesis testing, iterative refinement. The yakhchal is evidence that scientific thinking predates scientific institutions by millennia, that humans have always been capable of understanding their environment and manipulating it with precision, that the absence of formal theory does not mean the absence of knowledge, and yet we almost lost it entirely. If not for the structures themselves, massive and durable enough to survive abandonment, the full details of yakhchal operation might have disappeared. Many did. The written records are sparse. Persian engineers did not publish papers, they trained apprentices, they built. And when the need vanished, so did the practice. Modern understanding of yakhchals comes largely from archaeology, from studying the ruins and reverse engineering the principles, from talking to the last generation of people who remember seeing them in use. This is the fragility of human knowledge. It is not just written in books. It is embedded in practice, in living traditions, in the continuity of use. When that continuity breaks, reconstruction becomes archaeology, and archaeology is always incomplete. Today, climate scientists and sustainable architecture researchers study yakhchāls with renewed interest, not as historical artifacts, but as potential models: passive cooling, radiant heat loss, thermal mass. These are principles suddenly relevant again as energy costs rise and climate change makes traditional air conditioning increasingly unsustainable. The idea that you could cool a space, could make ice without electricity, without fuel, just through careful design and an understanding of natural processes, that idea has modern application. Some engineers are building new structures based on yakhchal principles, modified for modern materials, integrated with contemporary systems, but optimized for the same fundamental physics that Persian builders understood viscerally. The irony is not lost. We are rediscovering, through computer models and thermodynamic simulations, what ancient engineers knew through observation and experience. We are validating their work with our theories, and in some cases, we are finding that our modern equivalents are less efficient, more expensive, more complex than the originals. There is a hubris in modernity, an assumption that newer is better, that progress is linear, that ancient civilizations lacking our tools and theories must have been primitive. The yakhchal challenges this. It is a reminder that intelligence is not the same as technology level, that sophistication can exist without computers or laboratories or peer-reviewed journals, that people 3,000 years ago were just as clever, just as observant, just as capable of innovation as anyone alive today. They simply had different tools, different constraints, different contexts, and different priorities. The yakhchal was not built for profit maximization or market dominance. It was built to solve a fundamental problem of human survival in a harsh environment. It was infrastructure in the truest sense, a public good, something that elevated quality of life for an entire civilization. The largest yakhchals were communal, villages shared them. Cities maintained them as essential services, like water systems or grain stores. There was commercial use, certainly. There was elite consumption. But the technology itself was broadly accessible because it was locally buildable and maintainable. Contrast that with modern refrigeration, dependent on global supply chains for components, requiring electrical grids, needing specialized technicians for repair, producing refrigerants that deplete ozone or contribute to greenhouse warming. Functional, certainly, ubiquitous, but also fragile in ways a yakhchal never was. If the power grid fails, modern refrigeration stops. If supply chains break, replacement parts disappear. The system works brilliantly until it doesn't. And when it fails, most people have no idea how to fix it or replace it. The yakhchal could be built with local materials by local labor, using local knowledge. It had no external dependencies. It could not be turned off or shut down by distant authorities. It was, in a very real sense, resilient in ways modern systems are not. This is not an argument for abandoning progress. It is an observation about what we have traded away: complexity for simplicity, dependence for autonomy, specialization for broad competence. These trades have brought enormous benefits, but they have also created vulnerabilities, and the yakhchal, standing silent in the desert, is a monument to a different set of choices. The last traditional yakhchal to operate commercially in Iran closed in the 1960s. The man who ran it, whose father and grandfather had run it before him, was interviewed years later. He remembered the work, the precision required, the timing, how you knew when conditions were right for ice formation, how you managed the thermal mass, how you rationed the ice through summer. He said it was hard work. He did not romanticize it, but he also said it worked, reliably, year after year. And when electric freezers came, they were easier, faster, but also expensive to run, expensive to repair, and dependent on power that sometimes failed. He kept the old knowledge, taught it to his son, even though there was no practical use for it anymore. Just in case, he said. Just in case someone needed it again. That phrase echoes. Just in case. What other knowledge are we one generation away from losing? What other technologies, proven over centuries, have we abandoned in favor of systems that might be more convenient, but also more fragile? How many yakchāls, metaphorical or literal, exist in the archaeological record of cultures around the world, representing solutions we have forgotten because they did not fit the industrial model of progress? And perhaps more urgently, as we face challenges of sustainability and resource scarcity and climate adaptation, how much ancient knowledge could we be rediscovering instead of reinventing? How many problems have already been solved in different contexts with different tools, in ways we have simply forgotten to remember? The yakhchal made ice in the desert for 2,000 years. It worked. It was infrastructure. It was science. It was a solution so elegant that its principles remain valid today, studied by engineers trying to build a more sustainable future. And yet, for all that time, most of the world either did not know it existed or did not believe it could work. Knowledge, it seems, is not enough. Knowledge must be transmitted, practiced, valued, maintained. The structures still stand, dozens of them, scattered across Iran and neighboring countries. Their domes rise from the landscape like beehives, like monuments, like questions. Built by people whose names we do not know, using knowledge we nearly lost, solving problems we are only now remembering we have. They do not make ice anymore, but they still teach, still demonstrate, still challenge our assumptions about what is possible and what has been forgotten.